All right, so here we are with lesson number 2 of our first unit on science foundations. You should have a page of Cornell style notes in front of you. The title for this lesson is Interpreting Evidence. Your key question will be, how do we use data to come to a logical conclusion? Before we get started, these are the key questions you're going to want to think about. You don't really need to write these down. Just think about these, get your brain ready, prepare yourself for learning. But how do you take metric measurements? What is a metric conversion and how do you do them? How do you interpret different types of graphs? And finally, how do you draw conclusions using logic and evidence? First of all, we start with how we're going to be doing measurements in our class. Nearly every scientist on Earth takes measurements with the metric system. Believe me, the metric system is far better than the American system, which is known as the imperial system. There's a couple reasons. Number one, the metric system is based on the number 10. So all the conversions use the powers of 10 and don't make you do any math. The second one, metric uses the same base units. Doesn't matter the size of the base unit. I'm sorry, it doesn't matter the size of the measurement, the base unit stays the same. You just add a prefix. So in America, we have a gallon of milk, but then a pint of something and a quart and a liter and a cup. I don't know. Oh, and a fluid ounce. I don't know what any of those are really. If you're talking about distances, an inch becomes a foot becomes a yard becomes a mile. And again, you have to do math in addition to knowing all the words. Metric, you know the base unit, then you know all the different sizes of that measurement. You're going to want to know the metric base units right there, as you can see. If you already know these from, say, middle school, then you don't need to write them down. But if you do not know these, then it'd be a good idea to copy that chart into your notes. We measure distance in metric with something called meters. We'll talk about that. We measure volume. Usually we talk about volume as it relates to liquids, but that's measured in liter. If you've ever been to across the border into Mexico, you probably see a gas station selling gasoline by the liter. That's why the gas price is a little bit different. Mass is in grams, not pounds. Time, obviously, still in seconds. And then temperature is in Celsius. So if someone says, what's your temperature? And someone says 98 to someone who is measuring in Celsius, that means you're boiling. So the temperatures are quite different. So here are the base units you're going to need to know. If you do not know the base units, you're going to want to write this down. Copy this chart into your notes. You may even want to pause the video to make sure you can get them all. But they start with kilo, which means 1,000, hecto, which means 100, deca is 10, and then of course you get your base unit, which is basically 1. Then deci is a tenth, centi is 100th, and milli is 1,000. To help you remember that, or to show you what those mean, we have a video.
The metric system is a system of measurement used throughout the world, and especially in the scientific community. It is based on tens and can be easy and helpful to use. Let's begin with some basic units of measurements used in the metric system. Let's start with 7 frequently used units of the metric system. Starting at the left and moving to the right, we have kilo, hecto, deca, base, deci, centi, and then milli. Starting at the base unit and moving to the left, the deca would have a value of 10, a hecto would have a value of 100, and a kilo 1,000. Next, if you start at the base, which would have a value of 1, and move to the right, a deci would be 1/10, centi is 100th, and milli is 1,000th. Next, let's talk about the base unit. There are 3 main base units, and they give you a clue as to what is being measured. If you see a meter, it is for length, a liter is used for volume, and a gram is used for measuring mass. All three of these base units are related. A meter is 1/10,000,000th the distance from the North Pole to the equator on a meridian that passes through Paris. If you take this distance and divide it into 10 million small segments, you get a meter. If you then divide the meter into 10 equal parts, you have 10 decimeters. If you divide the decimeter into 10 equal parts, you have a centimeter. And then if you subdivide the centimeter into 10 small parts, you have a millimeter. On the other hand, if you have 1,000 meters, you have 1 kilometer. A liter is the volume of 1 cubic decimeter. So you can see how the three base units are related. A liter, the volume of 1 decimeter. Again, you can subdivide the liter into a centiliter, which is 1/10 of a liter. Finally, a gram is equal to the mass of 1 cubic centimeter of water. Finally, let's look at one more example of how the metric system works. Say for instance you measured a distance of 5 kilometers. Well, this would be equal to 50 hectometers, 500 decameters, 5,000 meters, 50,000 decimeters, 500,000 centimeters, and 5 million millimeters.
Alrighty. So hopefully that helped a little bit. Now we get into metric conversion. So what a conversion is to help you understand with American units, and then we'll move to metric. If someone told you this item that I'm measuring is 19 inches, and you needed to tell the person how many feet that is called a conversion. 19 inches is equal to a certain number of feet. And if you're curious, it's 1.1 foot and 7 inches. Or if you say, I have 9 feet, how many yards is that? That would be 3 yards. So that's the basic idea of what a conversion is. It's figuring out how much one amount is in one unit equal to another unit. So we do these in metric. In order to do these very easily, just remember that King Henry died unexpectedly drinking chocolate milk. That sentence matters. I'll explain why in a second. So to do a metric conversion, first you figure out where you are starting, and that's the number you're given. You then either move your finger or your pencil the number of spaces you're going to be going, and I'm going to have a video here to show you in a second. Then you count those number of jumps and in what direction. You go back to the number you were given, and you move the decimal the same number of places. And then there's a note down there at the bottom that says, remember the base unit in the middle does not have a prefix, but you need to include a jump for it. So to help you with that, here is a little video.
King Henry died unexpectedly drinking chocolate milk. This stands for kilometers, hectometers, decameters, your unit, which could be also M, G, or L, decimeters, centimeters, or millimeters. So we're converting from meters to centimeters. So I'm going to count how many spaces I'm going to move over. I'm going 1, 2 spaces from my M to my C. In this case, I'm going to move over two spaces to the right as well. Going 1, 2 spaces to the right. So my final answer will be 688 centimeters. My next one, I'm doing it in black pen. For my next one, I'm going, let's do number 3, meters to millimeters. I'm going from my unit, my M, to my millimeter. I'm going 1, 2, 3 spaces to the right. So I'm going to go 1, 2, 3 spaces to the right. Now I ran out of space, so I have to add a placeholder 0, 5,530 millimeters.
This is a pretty good way to explain how to do metric conversion. So you may want to go back and rewatch this. You could even do some of the other ones that are on that page as little sample problems, but let's go ahead and do a practice one. So take a look at what I have there. as a sample problem. And what I think you should probably do is try to do this on your own in your notes or on a separate sheet of paper. And then you can pause the video, work it out, and restart the video once you think you've got the answer and see if you're right. So what we're going to be doing is converting 2.3 kilometers. The K stands for kilo, the M stands for meter, and we're converting to a certain number of meters. Meter is a base unit. It's the U position on that chart. Go ahead and pause the video, work this out, move the decimal the direction you think it goes. And then when you're ready, when you're done, when you have an answer, unpause the video. So here's how you find the solution. First of all, the K in km is where you start. And I'm given 2.3 km. So I start on the K. As you can see on the far left, you see kilo. And in purple, which is like lavender, purplish pink. Anyway, in purple, you can see the number of jumps. I call it jumps, but the number of spaces we need to move or jump. So you go from kilo to hecto is 1, hecto to deca is 2, deca to the base unit or U is 3 jumps. You go back down and look at the very bottom of this page. You have 2.3. You're going to move the decimal 3 spaces to the right. Those final 2 pink zeros at the bottom, those are placeholder zeros. They are places where the decimal moved or it jumped and there wasn't a number there. So when there's no number there, you have to put a 0 in. So the final answer is 2,300 meters. You're going to be doing some of these as well as we move forward. Now, looking at data can be challenging. So we got all this data, you take it on these measurements. A much better and easier way to look at data is to organize it into a graph. Graphs show us things like trends, preferences, tendencies, and proportions. And then we use these graphs to make interpretations. Interpretations explain what the results of an experiment or a study mean. So for example, if I give 2 groups of patients who are suffering from a fever, 2 different medicines, or maybe a medicine and a placebo, and the group that received a certain medicine saw their fever go down faster than the other group, my interpretation of that data would be the medicine worked. That's a very simple interpretation. Scientists must be careful that their own bias does not affect their interpretations. So we need to have a little bit of practice from that. So different graphs show different things, but there are some important things that are in common. So I have a video to show you the things that are in common in all graphs.
Every graph, if done correctly, should have a title. The title should describe what is shown on the graph. In this case, the dark fur allele frequency in a field mouse population over time. Every graph should also have appropriately labeled axes. There is the x-axis, in this case, it is time in years, with the years labeled from 2008 to 2014. Every graph also has a y-axis, that is the vertical one. This y-axis is the allele frequency expressed as a percent, here from 10% to 60%. Now let's look at how to interpret what we see on the graph. Each point represents a coordinate where a percentage was measured, for example, 10% in a given year, here 2008, or approximately a little over 20% in 2010, up to about 60% in 2014. So you can see that this graph does show the change in allele frequencies over time. If you were asked, for example, what was the approximate frequency of the dark fur allele in 2011, this is how you would find it. Go to 2011 on the x-axis, and then measure up until you hit the line, and then measure over to the y-axis. This shows that in 2011, the dark fur allele frequency was approximately 30%, just a little bit higher. You can also do this from the other direction. That is, if you are asked in what year Did the dark fur allele make up 50% of the population? You go to the 50% on the y-axis, draw across, and then down to the x-axis, and you would see that it is approximately 2013, sometime during 2013, when the 50% mark was reached. So this is how you interpret graphs to discover biological trends.
Obviously, that was a biology teacher. We will be doing chemistry trends mostly. So we use logic and evidence to interpret graphs. For example, this is a graph of COVID-19 infections in California. And these are new cases. So the number of new people that have COVID. And as you can see, this was the most recent data for this was January 17th. And we had 31,617 in the entire state. But what does this graph tell you? Well, let's walk through it. First of all, we started in March and there wasn't very many cases. We saw the cases gradually rise until we got to, say, July. After July 12th, it took a bit of a dip into the beginning of August. It went up a little bit again at the start or the end of August, beginning of September, and then it started going down again. But then look at November 9th, and you could see the upward trend of COVID cases. Well, the next thing you have to ask is that out of the ordinary? Is that not what is common? Well, let's take a look at a graph of the entire United States. And as you can see, I'm going back and forth here. They are nearly identical. They even have that little hill on July or in July the same way. So what does that tell us? Well, that tells us that California is kind of suffering through the same infection rate as the entire US. But then we can look at additional data. This is a graph of the state of Hawaii. You'll notice that that mountain in the middle is the same exact place like July 9th on this graph and July 12th on this graph, where we had a big increase, or not a big increase, but at least an increase. It was much bigger in Hawaii. But then look what happened. It went down into September, and this continued going down, or kind of went down in November, and they're seeing a bit of an uptick, but nothing like in the United States or California. So then once you have that information, you have to ask yourself, or what we would then ask ourselves is why? How does that happen? And you would then use that to determine, well, this happened in Hawaii because X, Y, and Z. I will tell you, Hawaii has greatly limited the number of travelers allowed on the islands. And I believe they've actually instituted some other policies to stop the spread in Hawaii. So maybe then you want to look at Hawaii and see what they did and see why they were able to avoid the same spike that started right around the middle of November. And then sometimes graphs get really complicated, and take a look at this graph. What this is showing you is the rate of people not wearing a mask in a place in Kansas. And then you have the blue line, which is the number of cases. So if you notice, in May, the rate of mask wearing is pretty low, or I should say the rate of no one or not wearing a mask was pretty high. And as a result, we had a increase shortly thereafter of cases. But when, look on the far right, when the number of people wearing I'm sorry, not far right, in the middle, as the number of people who masked increased, the number of people not wearing a mask decreased, then the number of cases kind of leveled out. Now, if you look to the right, what I was going to mention is the number of non-mask wearers are actually higher now than they were back in May. So then we would make, hypothetically, a prediction that would say we might very well see an increase in cases sometime in the near future. And this graph cuts off right at the end of October, beginning of November. So we would then want to follow that up and study that. However, you need to be a discerning consumer of information. Not every graph is completely honest, and sometimes there are other factors. So here is a video to show you what happens when you have dishonesty in statistics.
Statistics are persuasive, so much so that people, organizations, and whole countries base some of their most important decisions on organized data. But there's a problem with that. Any set of statistics might have something lurking inside it, something that can turn the results completely upside down. For example, imagine you need to choose between two hospitals for an elderly relative's surgery. Out of each hospital's last 1,000 patients, 900 survived at Hospital A, while only 800 survived at Hospital B. So it looks like Hospital A is the better choice. But before you make your decision, remember that not all patients arrive at the hospital with the same level of health. And if we divide each hospital's last 1,000 patients into those who arrived in good health and those who arrived in poor health, the picture starts to look very different. Hospital A had only 100 patients who arrived in poor health, of which 30 survived. But Hospital B had 400, and they were able to save 210. So Hospital B is the better choice for patients who arrive at hospital in poor health, with a survival rate of 52.5%. And what if your relative's health is good when she arrives at the hospital? Strangely enough, Hospital B is still the better choice, with a survival rate of over 98%. So how can Hospital A have a better overall survival rate if Hospital B has better survival rates for patients in each of the two groups? What we've stumbled upon is a case of Simpson's paradox, where the same set of data can appear to show opposite trends depending on how it's grouped. This often occurs when aggregated data hides a conditional variable, sometimes known as a lurking variable, which is a hidden additional factor that significantly influences results. Here, the hidden factor is the relative proportion of patients who arrive in good or poor health. Simpson's paradox isn't just a hypothetical scenario. It pops up from time to time in the real world, sometimes in important contexts. One study in the UK appeared to show that smokers had a higher survival rate than non-smokers over a 20-year time period. That is, until dividing the participants by age group showed that the non-smokers were significantly older on average, and thus more likely to die during the trial period, precisely because they were living longer in general. Here, the age groups are the lurking variable and are vital to correctly interpret the data. In another example, an analysis of Florida's death penalty cases seemed to reveal no racial disparity in sentencing between black and white defendants convicted of murder. But dividing the cases by the race of the victim told a different story. In either situation, black defendants were more likely to be sentenced to death. The slightly higher overall sentencing rate for white defendants was due to the fact that cases with white victims were more likely to elicit a death sentence than cases where the victim was black, and most murders occurred between people of the same race. So how do we avoid falling for the paradox? Unfortunately, there is no one-size-fits-all answer. Data can be grouped and divided in any number of ways, and overall numbers may sometimes give a more accurate picture than data divided into misleading or arbitrary categories. All we can do is carefully study the actual situations the statistics describe and consider whether lurking variables may be present. Otherwise, we leave ourselves vulnerable to those who would use data to manipulate others and promote their own agendas.
So the takeaway obviously from that is you want to be a good discerner of information. Don't necessarily believe a Instagram post that claims to be telling you the truth. So please make sure you analyze, that you scrutinize as a consumer of information as you get older. Now, let's go back to our key questions. After this lesson, do you now know how to take metric measurements? Do you know what a metric conversion is, and could you do one? Do you know how to interpret a graph? And then finally, do you know how to draw conclusions using logic and evidence as opposed to just believing whatever was said? So what I want you to do right now is go ahead and finish up your notes. Go over to the left side. Condense your notes, all the notes you just took, however many they were. Condense them down into bullet points, short little, easy to study facts on the left side of your notes, and then put your notes aside, go do something else, come back to your notes later, and write a 2 to 3 sentence summary of everything you just learned. When you're done with that, you are done with this lesson, and once again, thank you for your attention.